Hey, welcome to the first lecture on linear algebra. Our linear algebra journey starts with matrices. Do you know what's a matrix? A matrix is a collection of numbers ordered in rows and columns, like this one, for example. This matrix contains the numbers 5, 12, 6, -3, 0, and 14. Each of these values is an element of the matrix. So, our matrix has a total of 6 elements. To make it clear, we are dealing with a matrix. We put all the elements in brackets. We would normally denote a matrix with a capital letter, for instance, A. Our matrix A has 2 rows and 3 columns. In linear algebra, rows and columns are the 2 dimensions of the matrix. A has 2 rows and 3 columns, so we say its dimensions are 2 and 3, or better, A is a 2 by 3 matrix. Normally, we would take note on that and put it below the letter A. Okay, matrices may seem like tables and spreadsheets at first. However, the purpose of matrices is not simply to store values, but to be main characters in mathematical operations. 2 matrices can be summed, subtracted, multiplied, and divided. So linear algebra is similar to algebra in the types of operations there are, but differs in how and when these operations are implemented, and if they are permitted at all. We will discuss all of that at length in this section. Okay. A matrix can only contain numbers, symbols, or expressions, with the idea that the latter 2 are nothing more than a generalized representation of numbers. For instance, the collection of these 6 symbols, A, B, C, D, E, F, show a different 2 by 3 matrix, say B. Here's another one. C. C has 4 elements and is a 2 by 2 matrix. Its incumbents, however, are not values, but expressions. Great! What about the size of a matrix? Matrices can be of any size. In the general case, we are talking about an m by n matrix. If A is an m by n matrix, then this means it has m rows and n columns. Sometimes we need to reference a particular element of A. The elements of A are denoted with a lowercase a and 2 numbers indicating the respective element position in terms of row and column. For instance, Aij is the element at position ij, where I is the respective row and j is the respective column. Therefore, if we want to fill in the matrix, it would start from A11, then A12, A13, until A1n to finish the first row. Similarly, we've got A11, A21, A31, until AM1 to complete the first column. The last element of the matrix is AMN. The total number of elements is m times n. Okay, great! To finish off this introductory lecture, we must note that in most programming languages, albeit not all of them, arrays start from 0 rather than 1. In Python, for instance, arrays start from 0, so keep that in mind when coding. All right, in our next lecture, we will look into vectors. Thanks for watching. In the last lesson, we looked at matrices. What you may have noticed is that matrices are 2-dimensional objects by definition, as they have rows and columns. However, there are specific cases of matrices which are also widely used. One of them is overwhelmingly common. A matrix with 1 row and 1 column. Naturally, it contains a single element. That's called a scalar. In fact, all numbers we know from algebra are referred to as scalars in linear algebra. For instance, the number 15 is a scalar. So are 1, 2, -5, pi, and so on. Since scalars are objects with no dimensions, they have important properties we are going to examine later on. For now, we just need to introduce the basic terminology in order to be able to dive into linear algebraic operations. All right. Next on our list are vectors. Vectors are also very common objects in linear algebra. They sit somewhere between scalars and matrices as they have one dimension. Here's a vector with three elements, 5, -2, and 4. Notice that this vector is nothing more than a 3x1 matrix. Its single dimension is the number of rows it has. Since a scalar is basically a number, a vector is practically the simplest linear algebraic object. Due to the many applications of vectors, they have this special name and are often examined as a separate object. Moreover, it is more common to view a matrix as a collection of vectors rather than a vector as a special case of a matrix. Okay. Generally, there are two types of vectors, row vectors and column vectors. We just explored a column vector. Logically, we can have row vectors like this one, 3, 4, 5, 8. Often, we are interested in the number of elements a vector contains. We refer to that number as the length of the vector. The first vector we saw had a length of 3, while the second one, a length of 4. Okay, great! In the general case, a vector's length can be designated as m. So, a column vector would have dimensions m by 1, and a row vector 1 by m. Regarding the notation, the elements of a vector x would be x1, x2, until xm. Let's summarize. We have matrices that have two dimensions, m by n. Vectors that have a single dimension, m by 1. And scalars that have no dimensions and are 1 by 1. In the consequent lectures, we will learn how to add, subtract, and multiply matrices, vectors, and scalars, which will make these concepts even more intuitive. Thanks for watching. Let's have a short lecture about geometry. More often than not, mathematics works based on analogies. With linear algebra, that's extremely relevant. We said that a scalar has no dimensions. What else has no dimensions that you can think of? Well, the geometrical idea of a point. A point is obviously the simplest object in terms of geometry. It has no direction nor size. A scalar is like a point. Then we have vectors. A vector has one dimension. It's like a line. However, it has a direction. It can be oriented in many ways. I would really like to plot this on a two-dimensional plane. However, to get into 2D, we need something else. The only way to get from a line to a plane is by crossing it with another line, right? So, two-dimensional space is defined by two lines. Well, two lines means two vectors. And in linear algebra, a matrix is a collection of vectors. Therefore, any two-dimensional plane can be represented by a matrix. This idea is very simple, yet extremely powerful. Let's explore the two-dimensional plane. If I want to represent a vector, say 2, 5, it would be a line from the origin of the plane to the point of position 2, 5. The direction is always from the origin of the graph to the endpoint. The vector -2, -5 would be exactly the opposite of the first one. The vector -2, 3 would appear the following way, and so on. As you can see, each of these vectors has a direction determined by its values. Okay. By the way, this vector is 1, 0, while the other one 0, 1. Taking these two vectors together, we can create a matrix. 1, 0, 0, 1. This matrix is basically made up of small portions of the two axes, x and y. What's important, though, is that if I remove everything else from the graph, this matrix would define the two-dimensional plane we were just looking at. Actually, every two vectors I take would define the 2D plane we are looking at. In fact, for you watching the course, all these matrices are defining the plane of your screen right now. Cool! A nice free online tool to play around with is the 3D Vector Plotter by academo.org. You can specify each vector of interest and fiddle with the plots. This website allows you to create all kinds of matrices up to 3 by 3. In this way, you will get a better grasp of the geometrical concept accompanying vectors and matrices. Great! Let's get out of geometry and back to linear algebra. Note that you can come back to this lecture at any future point and look into these ideas with fresh eyes. Thanks for watching. Hey! After we explore the geometry of linear algebra, it is time for yet another point of view, the programming one. If you want to get into data science, that's going to be the context in which you will need linear algebra. So, let's open a Jupyter notebook and see how we can code a matrix, a vector, and a scalar. The simplest and most flexible way to work with scalars, vectors, and matrices in Python is by using arrays. Moreover, we'll use the NumPy functionalities as they are optimized for such operations. I'll import NumPy as NP. Okay. Let's start by declaring a scalar. In Python and many other languages, an integer or a float are doing the job. So, s equals 5 will do. Time for something more sophisticated. How would we declare a vector? Say we are looking at the same vector as before, 5 minus 2 and 4. Let's declare a new variable v equal to np array of 5 minus 2 and 4. Note that there are round brackets for the np array method and square brackets for the vector itself. Printing v, we would see that it contains the 3 values we wanted. Cool! We have created a vector. By default, v is a row vector. All right. Finally, let's create a matrix. M equals np array of round brackets. Now, if you think about it, this matrix actually contains 2 vectors, this one and that one. In fact, that is how we would go about declaring it. Square brackets, 5, 12, 6, close the brackets, comma. Square brackets, -3, 0, 14, close all brackets. Here. As you can see, we have a matrix, exactly as we wanted. These tasks are quite simple, but please feel free to practice later on. However, there are several important programming considerations we need to make. We will focus on them now as they are paramount for coding. First, data types. If we write type, brackets, and then a variable, we would obtain the data type of that variable. Type s. So, s is int, or an integer. V and M are ND arrays. ND array stands for an n-dimensional array. More specifically, the vector v is a 1-dimensional array, while the matrix M is a 2-dimensional array. In general, we can have n-dimensional arrays, which we will talk about later on. All right. Finally, if I want s to be consistent with the others, I can actually declare it as an array too. s underscore array equals np array of 5. Checking its data type again, we will see it is an ND array. And that's another way you can create a scalar in Python. For all practical purposes, in Python and within NumPy, integers or floats and arrays with one element behave in the same way regarding linear algebraic operations. All right. What about the shapes of the variables? There is a method called shape, which we can apply to our objects to check their dimensionality or shape. m.shape returns 2 by 3. That's also the expected result, as we are dealing with a 2 by 3 matrix. v.shape returns 3, comma. This is something which you are likely to see in some programming languages, but not all. It is basically indicating that in the memory of the computer, this object has 3 elements. The elements are stored in order, though. Depending on our needs, we could use the reshape method to create a row or a column vector. V dot reshape and the form we want. There are two possibilities, 1, 3, and 3, 1. The first gives us a row vector, the second, a column one. Okay. Finally, we can check the shape of S. We get an error, as int objects don't have shape. Trying the same method on S array, we simply have parentheses. That's because a scalar is a zero-dimensional object, thus it has no shape, precisely like the point we discussed in the previous lesson. Cool! That's more or less how we can declare and think about matrices, vectors, and scalars in Python. In the next lectures, we will explore new concepts and practice them with code. Thanks for watching! In the last parts of our program, we make use of the state-of-the-art deep learning framework developed by Google called TensorFlow. TensorFlow works in a peculiar way, but one of its main characteristics is that it works with tensors. So, it is only right that we introduce tensors now. The mathematical concept of a tensor could be broadly explained in this way. A scalar has the lowest dimensionality and is always 1 by 1. It can be thought of as a vector of length 1 or a 1 by 1 matrix. It is followed by a vector, where each element of that vector is a scalar. The dimensions of a vector are nothing but m by 1 or 1 by m matrices. Okay. Then we have matrices, which are nothing more than a collection of vectors. The dimensions of a matrix are m by n. In other words, a matrix is a collection of n vectors of dimensions m by 1, or m vectors of dimensions n by 1. Furthermore, since scalars make up vectors, you can also think of a matrix as a collection of scalars too. We know all that already. Let's get to tensors. Now, a tensor is the most general concept. Scalars, vectors, and matrices are all tensors of ranks 0, 1, and 2 respectively. Tensors are simply a generalization of the concepts we have seen so far. An object we haven't seen is a tensor of rank 3. Its dimensions are k by m by n. It can be thought of as a collection of matrices. In terms of programming, a tensor is no different than an ND array. And in fact, tensors can be stored in ND arrays, and that's how we often deal with the issue. Let's create a tensor out of two matrices. Our first matrix, M1, will be from the first example. The matrix M2 will be a different one with the elements 9, 8, 7, and 1, 3, minus 5. Now, let's create an array, T, with two elements, M1 and M2. After printing T, we realize that it contains both matrices. It is a 2 by 2 by 3 object. It contains two matrices, 2 by 3 each. All right. If we want to manually create the tensor, we would need to write this line of code. As you can imagine, tensors with lots of elements are very hard to manually create, not only because there are many elements, but also because of those confusing brackets. Usually, we would load, transform, and pre-process the data to get tensors. However, it is always good to have the theoretical background. This will do for now. Thanks for watching. Similar to normal algebraic operations, we can add and subtract matrices. Let's start with addition. This is an extremely easy operation. There is only one condition. The two matrices must have the same dimensions. Say we have the two matrices M1 and M2. M1 has elements 5, 12, 6, and minus 3, 0, and 14, and M2 contains 9, 8, 7, and 1, 3, and minus 5. As you can see, they are both 2 by 3 matrices. If I want to add the two, all I need to do is add the corresponding entries one with the other. The result is a new 2 by 3 matrix. For the element at position 1, 1, we have 5 plus 9. For the element at position 1, 2, we have 12 plus 8. We continue adding them until position 2, 3, where we've got 14 plus minus 5. All we have left is to make the simple calculations and reach the solution. 14, 20, 13 on the first row, minus 2, 3, and 9 on the second. And that's the result. Simple as that. If I want to add the matrices in Python, I'd need to declare them and simply use a plus sign. Cool! Now, as you are aware, subtraction is just a type of addition, so same rules apply there. Let's have these two matrices instead. In order to find the difference between the two matrices, we just need to calculate the differences between each two corresponding elements. Note that the two matrices have the same dimensions once again, this time 2 by 2. The final result is minus 2, 8 on the first row, and 5 minus 4 on the second. In terms of coding, things are no different. We declare the two matrices and find their difference. Okay, great! Finally, I'll give a different example, so you can see that we can do the same with floats as well. The two matrices are both 3 by 2, so they are compatible. Here's the result. What about vectors? Since vectors are nothing more than one-dimensional matrices, same rules apply. Let's take the vector 1, 2, 3, 4, 5 and the vector 5, 4, 3, 2, 1 and add them together. With vectors, we only care about the length. The two vectors have the same length, 5, so they are compatible. There is only one way to add them up. First element with first element, second element with second, and so on. The result is a vector of length 5, where all entries are 6s. What about the difference? It is a vector of length 5 with elements minus 4, minus 2, 0, 2, and 4. All right, let's wrap it up here. Please have a go at the practice problems after this lecture. Thanks for watching. Let's talk a bit more about scalars. Scalars are more peculiar than higher dimension objects because they are single numbers. We didn't talk about it, but you know very well how to add two scalars together, right? 5 plus 5 equals 10. 10 minus 4 equals 6. No biggie. You also know that in order to add vectors and matrices together, their forms must match. We are not allowed to add vectors of different length and matrices with different dimensions. Such operations are not permitted in linear algebra, and Python knows that. For instance, if I try to add a 2 by 3 matrix with a 2 by 2 matrix, we will get this message. Operands could not be broadcast together with shapes, and we will be shown the operands' respective shapes. Similarly, if I try to add two vectors with different lengths, I will receive the same error. Mathematically, these operations don't make sense, so they cannot be executed. Okay, there is one exception. Because of how arrays work in Python and many other languages, we can actually add scalars to matrices and vectors. For instance, if I add 1 to the matrix M1, you can see that 1 was added element-wise. In other words, each element was increased by 1. Similarly, if I add 1 to the vector v1, it will be added element-wise. Mathematically, this operation is not allowed as the shapes are different, but in programming, or at least in Python, it works. All right. It was very important to be aware of this peculiarity. Probably some of you may have already tried it and found out that it yields a result. The result has a meaning in terms of arrays, but not in terms of linear algebra. That is also one of the big differences between the concepts of ND arrays and tensors. In this lesson, we will discuss the transpose of a matrix. Let's start from vectors. We already know that vectors are either rows or columns. So, let x be the column vector 1, 2, 3. There is a special operation which can turn it into a row vector. We can transpose it. Transposing the column vector 1, 2, 3 would yield in a row vector 1, 2, 3. We denote this operation with the letter t as a superscript. Therefore, x transposed, or the column vector 1, 2, 3 transposed, equals the row vector 1, 2, 3. Cool! Let's see another one. The row vector 1, 2, 3 transposed equals the column vector 1, 2, 3. So, this is a pretty neat operation. If we transpose x twice, we get x. How about another example? The row vector 2 minus 2, 0, 5, when transposed, becomes the column vector 2 minus 2, 0, 5. Very easy, right? However, there are several very important considerations here. First, when we transpose a vector, we are not losing any information. The values are not changing or transforming, only their position is. Second, transposing the same vector twice yields the initial vector. Third, our initial vector, 1, 2, 3, had a length of 3. In other words, it was a 3 by 1 matrix. By transposing it, it remained a vector of length 3, but it became a 1 by 3 matrix. This last consideration gives a peek into how transposing works for matrices. It turns all its rows into columns and vice versa. In terms of dimensions, when transposed, an m by n matrix becomes an n by m matrix. Let's check out an example, shall we? Here's the matrix A. 5, 12, 6 on the first row, and minus 3, 0, 14 on the second row. A transposed equals 5 minus 3 on the first row, 12, 0 on the second, and 6, 14 on the third. A is a 2 by 3 matrix. A transposed is a 3 by 2 matrix. We can see that the first column of A became the first row A transposed. The second column of A became the second row of A transposed. And the third column became the third row. This is how we transpose a matrix. The initial matrix A is nothing more than a collection of two row vectors, 5, 12, 6, and minus 3, 0, 14. Transposing the matrix A means transposing each of those vectors and putting them back together. So transposing matrices is nothing more than transposing a bunch of vectors. All right, let's get in Jupyter and see how this works out there. I'll first declare A as an NP array. In order to get the transpose of A, we simply write A dot capital T. That's all. Great! We will see two more examples just to solidify the knowledge. Taking the 2 by 2 matrix B containing 5, 3, minus 2, 4, and transposing it, we get another 2 by 2 matrix, this time 5, minus 2, 3, 4. Okay, finally, this 4 by 2 matrix, C, when transposed, equals that one. Again, notice that this operation is nothing more than transposing several vectors one by one. Right. Here are some further clarifications. Any scalar, when transposed, equals itself. Scalars are not the most interesting concepts, you see. So let's move on to vectors. We have the vector x equal to 1, 2, 3. Transposing it would yield the same result. That's because in Python, one-dimensional arrays don't really get transposed. Remember its shape? It is 3, comma. If I reshape it into a 3 by 1 matrix or a two-dimensional array, I will be able to transpose it though. That's another peculiarity you must consider when working with ND arrays in Python. Okay, great! In the next lecture, we will explore multiplication. Thanks for watching. We have reached an important milestone: multiplication. Let's start from the simplest one, scalar multiplication. 5 times 6 is 30. 10 times minus 2 is minus 20. I think these 10 seconds on it are enough. It is much more interesting to investigate vector multiplication. So, let's take these two vectors. 2, 8, minus 4, and 1, minus 7, 3. If we want to multiply them, the condition is they must be compatible, or in other words, have the same length. All right. There are two types of products we can get. One is called dot or inner product, while the other, outer or tensor product. Here, we won't be needing the outer product, so you can read about it on your own if you wish. The dot product, however, is heavily used. When people talk about multiplying vectors and matrices, that's what they mean. Other popular names for the dot product are inner or scalar product. The notation is a dot, signifying it is the dot product. It works like this. We multiply each two corresponding elements and find their sum. For our case, the expression is as follows: 2 times 1 plus 8 times minus 7 plus minus 4 times 3. The result is minus 66. As you can see, we multiplied two vectors and got a scalar. That is why we also call the dot product scalar product. By the way, note that the dot product is nothing more than the sum of the products of the corresponding elements. In Python, we would need to declare the two vectors. Next, we will use the method dot provided by NumPy. So, np dot xy. This will give us the dot product, which is minus 66. Okay, let's see another example just to make sure you get the concept. The dot product of the vectors 0, 2, 5, 8, and 20, 3, 4, minus 1 is 0 times 20 plus 2 times 3 plus 5 times 4 plus 8 times minus 1. The result is 18. That's all. What about the operations from the beginning of the lecture? 5 times 6 is 30. This was a scalar product of two scalars that resulted in another scalar. All right. Finally, what happens when we multiply a scalar by a vector? Let's multiply. 5 times the vector, 2, 8, minus 4. When we multiply a vector by a scalar, we get a vector with the same length. Its incumbents are each multiplied by that scalar. So, for our case, we would get 2 times 5, 8 times 5, and minus 4 times 5. The result is 10, 40, minus 20. What's interesting is that the initial vector had been scaled 5 times. So, multiplication by a scalar doesn't change the shape, but only the scale of the values. Got it. That will do for now. In the next lecture, we will generalize this concept to matrices. Thanks for watching. Let's generalize the dot product notion to matrices. You can see this overly used matrix once again. 5, 12, 6, minus 3, 0, 14. If I want to multiply it by 3, we would have a scalar times a matrix situation. Similar to what we saw in the last lesson, the shape of the matrix doesn't change, it just gets scaled. We keep the shape and multiply each element by 3. The result is 15, 36, 18, minus 9, 0, 42. All right, that's easy. But how do we multiply a matrix with another matrix? Using the same concept, the dot product, we can multiply two matrices. There is a compatibility measure here too. We can only multiply a matrix of dimensions m by n with a matrix of dimensions n by k. Basically, the second dimension of the first matrix has to match the first dimension of the second matrix. So, we can multiply a 2 by 3 matrix with a 3 by 1 matrix. Actually, we can multiply it by a 3 by 2, 3 by 3, 3 by 4, and so on until 3 by k matrix. What's important is that those 3's are matching. Similarly, if I want to multiply a 5 by 7 matrix, compatible matrices for multiplication are 7 by 1, 7 by 2, 7 by 7, and so on. Okay, there. What about the dimensions of the product itself? When multiplying an m by n matrix with an n by k matrix, the output is an m by k matrix. For instance, a 2 by 3 matrix times a 3 by 6 matrix will give us a 2 by 6 matrix. A 3 by 4 matrix times a 4 by 2 matrix will give us a 3 by 2 matrix. A 100 by 300 matrix times 300 by 3 matrix will result in a 100 by 3 matrix. Basically, whichever dimension is repeating will disappear in the resulting matrix. Okay, now we know the compatibility measure. How do we actually multiply matrices then? Let's start with two matrices, 2, 8, minus 4, and 1, minus 7, 3. Actually, these are two vectors, or 3 by 1 matrices, right? In order to multiply them, they need to have matching forms. To find their dot product, we transpose the first one and get a 1 by 3 times a 3 by 1 form. This is done because when we have a dot product, we always multiply a row vector times a column vector. Remember that. The result of this multiplication is a 1 by 1 form, or a scalar. We reach this scalar by multiplying the corresponding elements and summing everything up. We've already talked about that, we just didn't know the concept was the same. All right. Time to take the two matrices and multiply them. The first is the same one from the beginning of the example. The second will be a 3 by 2 matrix. 2 minus 1, 8, 0, 3, 0. The first thing we need to do is check their compatibility. 2 by 3 times 3 by 2. The forms are matching, so we are good to go. The next step is to find the shape of the output matrix. The matching dimension disappears, so the resulting shape is 2 by 2. Finally, we must do that multiplication itself. Let me remind you two important things. First, matrices are nothing more than a collection of vectors. And second, when we have a dot product, we always multiply a row vector times a column vector. How does this apply to our case? Well, the first matrix is made up of two row vectors, 5, 12, 6, and minus 3, 0, 14. The second matrix is made up of two column vectors, 2, 8, 3, and minus 1, 0, 0. In order to find the dot product of the two matrices, we just need to find the dot product of the vectors they are made of. Let's find the dot product of 5, 12, 6, and 2, 8, 3. It is 5 times 2 plus 12 times 8 plus 6 times 3, which equals 124. Easy. 124 is also the first element of the output matrix. Next, we find the dot product of 5, 12, 6 with the second vector, minus 1, 0, 0. It is 5 times minus 1 plus 12 times 0 plus 6 times 0. The result is minus 5, which is the second element of the output matrix. Great! Let's get to the second row of the initial matrix. There we have minus 3, 0, 14. We repeat the same procedure. The dot product of the vector minus 3, 0, 14 and 2, 8, 3 equals minus 3 times 2 plus 0 times 8 plus 14 times 3. We get 36. This is the first value on the second row of the output matrix. Notice that the row vectors from the first matrix determine the row in the output matrix. In the same way, the column vectors from the second matrix determine the column of the respective value. Finally, we find the last dot product. We get 3, and the product matrix has been found. Great! In terms of code, things are very simple. We use the method np dot and the two matrices and immediately get the result. All right! While this lesson is getting a bit long, we should do another example just to solidify the knowledge. I'll take two big matrices, this one and that one. The first matrix is 4 by 5. The second matrix is 5 by 2. First things first, are the matrices compatible? Yes, they are. Second, what will the shape of the output matrix be? Of course, 4 by 2. Next, let's divide the first matrix into row vectors and the second matrix into column vectors. There is a total of 4 row vectors and 2 column vectors. In order to start multiplying, we must find the dot product of the first row vector and the first column vector. The result we get is minus 71. Next, we multiply the first row vector with the second column vector. We get minus 48. We continue in the known way until we fill the product matrix. All right, linear algebra doesn't seem that hard after all. Do you feel comfortable? Let's do one more. This matrix multiplied by that one. A 3 by 4 matrix times a 2 by 3 matrix. What will the dimensions of the output matrix be? 3 by 3, no? Wait. It's not 3 by 3. In fact, it's nothing. The two matrices are not compatible. It is very important to remember that more often than not, you will not be able to multiply two matrices. So, please take good note of the shapes. Thanks for watching. We've seen a lot of matrix operations so far, but the big question for most of you remains: why is linear algebra actually useful? There are very many applications of linear algebra. In data science, in particular, there are several ones of high importance, which we will explore and use later on. Some are easy to grasp, others not just yet. In this lesson, we will explore 3 of them: vectorizing code, also known as array programming, image recognition, dimensionality reduction. Okay, let's start from the simplest and probably the most commonly used one: vectorized code. We can certainly claim that the price of a house depends on its size. Suppose you know that the exact relationship for some neighborhood is given by the equation price equals 10,190 plus 223 times size. Moreover, you know the sizes of 5 houses, 693, 656, 1,060, 487, and 1,275 square feet. What you want to do is plug in each size in the equation and find the price of each house, right? Well, for the first one, we get 10,190 plus 223 times 693 equals 164,729. Then we can find the next one, and so on until we find all prices. Now, If we have 100 houses, doing that by hand would be quite tedious, wouldn't it? One way to deal with that problem is by creating a loop. You can iterate over the sizes, multiplying each of them by 223 and adding 10,190. However, we are smarter than that, aren't we? We know some linear algebra already. Let's explore these two objects. A 5 by 2 matrix and a vector of length 2. The matrix contains a column of ones and another with the sizes of the houses. The vector contains 10,190 and 223, the numbers from the equation. If we go about multiplying them, we will get a vector of length 5. The first element will be equal to 1 times 10,190 plus 693 times 223. The second two, 1 times 10,190 plus 656 times 223, and so on. By inspecting these expressions, we quickly realize that the resulting vector contains all the manual calculations we made earlier to find the prices. In machine learning and linear regressions in particular, this is exactly how algorithms work. We've got an inputs matrix, a weights or a coefficients matrix, and an output matrix. Without diving too deep into the mechanics of it here, let's note something. If we have 10,000 inputs, the initial matrix would be 10,000 by 2, right? The weights matrix would still be 2 by 1. When we multiply them, the resulting output matrix would be 10,000 by 1. This shows us that no matter the number of inputs, we will get just as many outputs. Moreover, the equation doesn't change, as it only contains the two coefficients, 10,190 and 223. This concept will turn quite helpful in your machine learning studies later on. All right, so whenever we are using linear algebra to compute many values simultaneously, we call this array programming or vectorizing code. It is important to stress that array programming is much faster. There are libraries such as NumPy that are optimized for performing this kind of operations, which greatly increases the computational efficiency of our code. Okay, what about image recognition? In the last few years, deep learning, and deep neural networks in particular, conquered image recognition. On the forefront are convolutional neural networks, or CNNs in short. What is the basic idea? You can take a photo, feed it to the algorithm, and classify it. Famous examples are the MNIST dataset, where the task is to classify handwritten digits, CIFAR-10, where the task is to classify animals and vehicles, and CIFAR-100, where you have 100 different classes of images. The problem is that we cannot just take a photo and give it to the computer. We must design a way to turn that photo into numbers in order to communicate the image to the computer. Here's where linear algebra comes in. Each photo has some dimensions, right? Say this photo is 400 by 400 pixels. Each pixel in a photo is basically a colored square. Give it enough pixels and a big enough zoom out causes our brain to perceive this as an image rather than a collection of squares. Let's dig into that. Here's a simple grayscale photo. The grayscale contains 256 shades of gray, where 0 is totally white and 255 is totally black, or vice versa. We can actually express this photo as a matrix. If the photo is 400 by 400, then that's a 400 by 400 matrix. Each element of that matrix is a number from 0 to 255. It shows the intensity of the color gray in that pixel. That's how the computer sees a photo. But grayscale is boring, isn't it? What about colored photos? Well, so far we had two dimensions, width and height, while the number inside corresponded to the intensity of color. What if we want more colors? Well, one solution mankind has come up with is the RGB scale, where RGB stands for red, green, and blue. The idea is that any color perceivable by the human eye can be decomposed into some combination of red, green, and blue, where the intensity of each color is from 0 to 255, a total of 256 shades. In order to represent a colored photo in some linear algebraic form, we must take the example from before and add another dimension, color. So instead of a 400 by 400 matrix, we get a 3 by 400 by 400 tensor. This tensor contains 3 400 by 400 matrices, one for each color, red, green, and blue. And that's how deep neural networks work with photos. Great! Finally, dimensionality reduction. Since we haven't seen eigenvalues and eigenvectors yet, there is not much to say here, except for developing some intuition. Imagine we have a data set with 3 variables. Visually, our data may look like this. In order to represent each of those points, we have used 3 values, one for each variable x, y, and z. Therefore, we are dealing with an m by 3 matrix. So, the point I corresponds to a vector xi, yi, and zi. Note that those 3 variables, x, y, and z, are the 3 axes of this plane. Here's where it becomes interesting. In some cases, we can find a plane very close to the data, something like this. This plane is 2-dimensional, so it is defined by 2 variables, say u and v. Not all points lie on this plane, but we can approximately say that they do. Linear algebra provides us with fast and efficient ways to transform our initial matrix from m by 3, where the 3 variables are x, y, and z, into a new matrix, which is m by 2, where the 2 variables are u and v. In this way, instead of having 3 variables, we reduce the problem to 2 variables. In fact, if you have 50 variables, you can reduce them to 40 or 20 or even 10. How does that relate to the real world? Why does it make sense to do that? Well, imagine a survey where there is a total of 50 questions. 3 of them are the following. Please rate from 1 to 5. 1. I feel comfortable around people. 2. I easily make friends. And 3. I like going out. Now, these questions may seem different, but in the general case, they aren't. They all measure your level of extroversion. So it makes sense to combine them, right? That's where dimensionality reduction techniques and linear algebra come in. Very, very often we have too many variables that are not so different, so we want to reduce the complexity of the problem by reducing the number of variables. All right, now that you are convinced this new knowledge is useful, let's go back to learn some more linear algebra. Thanks for watching.